In this lecture, we want to talk about a basis for a vector space Rn, or a basis for a subspace V that's contained in Rn. So the setup is this. V is a subspace of Rn, and it could be that V is actually equal to all of Rn. And we'll let S be a set of k many vectors in the subspace V. Again, could be Rn. So we will call this set S a basis for the subspace V if two things are true. First thing, the span of S is equal to all of V. In other words, S spans V. In other words, if you want to think about that geometrically, that means you can reach every point in V using only the directions in the set S, right? So all the points in V are reachable using only the directions / vectors in the set S. And the second thing is that the set S needs to be linearly independent. So geometrically what that means is that all the directions in S are required to reach every point in V. So in the span case, you may have more than what you need to reach every point in S. The linear independence says you've got exactly what you need to reach every point in S. So all of the directions are fundamentally different, right? There's no redundant directions in a linearly independent set. So again, we will call this thing a basis, right? It's called a basis if it does two things that you already know about. One, it's got to span all of V, and two, it's got to be linearly independent. All right, here are some examples, and let's try to use some geometric reasoning to see which of these sets of vectors will be a basis for all of R2. So, in the first example here, we've got two vectors in R2, and you can see they point in fundamentally different directions, and you can see that it generates a parallelogram whose area is not zero. So I could take this parallelogram and tile the whole plane, and eventually, right, any point in the plane, you can stack tiles to reach that point. So every point in R2 is reachable using these two vectors, right? There's two of them. Everything can be written as a linear combination of these two things, and they point in fundamentally different directions. So span, everything in R2 is a linear combination, and they're linearly independent. They point in two fundamentally different directions, right? i.e. they're not parallel. And then for this one, here you've got two vectors. So this is a basis, by the way. So these two vectors form a basis. So if you've just got U and V here, this will form a basis for R2. Here are two vectors in R2 that do not form a basis. So, and the reason is it doesn't span. Like, what's the span of these two vectors? Well, these vectors are collinear, they're parallel, and so the span of these two vectors is really just the span of one single vector. So the span is just a line, right? It doesn't fill up the plane. So this can't be a basis. These two vectors do not span the space, and they're not linearly independent. In fact, they're linearly dependent. So this example fails both span and linear independence. Here's a set of three vectors in R2. This thing is not a basis because there's too many of them. Remember, three vectors in R2 must be linearly dependent, right? So this thing is not linearly independent. They must be linearly dependent, so it can't be a basis. It does span, you know, if these two span all of R2 because they're in fundamentally different directions. Therefore, when you throw in a third one, all three of them will span all of R2. If anything in R2 is a linear combination of these two things, well then you can make anything in R2 a linear combination of this third thing. Like you could just do alpha U plus beta V plus 0 times W is equal to some point, say, PQ. Right, so three vectors is too many vectors in R2. It makes them linearly dependent, so it can't be a basis, right? Span is okay, Linear independence is not. So this is not a basis. And then here's a set with only one vector in it. So this thing, there's too few vectors to span all of R2. We've seen that. In R3, for example, you need at least three vectors to span. If you've got any fewer than three, it won't span. So here we've got one vector in R2, there's too few, so it won't span. But certainly one vector is linearly independent. So this is a basis, because it spans and is linearly independent. This is not a basis. It's neither a spanning set nor is it linearly independent. This thing is not a basis because it does span, but it is not linearly independent. And this thing is not a basis. It is linearly independent, but it does not span. So think about this geometry when you're working through problems, especially in R2 and R3, because you can actually visualize those spaces. All right, here's an example, and really this is more of a definition than an example. So let's let E2 be the set consisting of these two vectors, little e1, little e2, and what are these things? These are vectors in R2. So E1 is the first standard basis vector, right? So it's the one that points along the I-axis. Sometimes calculus books will call this thing I. And then here's E2 that is the unit vector along the positive y-axis. Some calculus books will call this thing J. And then if you've got in 3 dimensions, this thing is I, J, and K, right? You've seen that in calculus, or at least you will. I'm just going to call these things E1, E2, E3, so on and so forth. So E2, capital E2, the set of vectors consisting of these two vectors, is a basis for R2, right? These two vectors point in fundamentally different directions, and you can get to any point in the plane using these two things. So for example, if I take any vector in R2, any vector in R2 can be written as AB, where A and B are real numbers. This thing is certainly the scalar A times the unit vector 1, 0 plus the scalar B times the unit vector 0, 1. In other words, it's AE1 plus BE2. So these two vectors span the entire space R2. So that's part 1 of basis. And then part 2 of basis, are these two vectors linearly independent? Well, graphically we can see that yes, they are. How do you prove that algebraically? Well, show that 0, there's only one way to write 0 as a linear combination of these two things, and that's the trivial way. So you set up a vector equation, alpha 1, 0 plus beta 0, 1 is equal to 0. Work this out. This is the same thing as alpha beta. It's the vector alpha beta, alpha comma beta. So that's got to be equal to 0, 0. And that forces alpha to be 0, and it forces beta to be 0. So this set, E1, E2, or I and J, or these two basis vectors, are linearly independent. So that shows that E2 is a basis for R2. And this is called the standard basis, right? This is called the standard basis for R2. And so certainly we can generalize this to R3. So now let E3 be the vectors E1, E2, and E3. And yes, E1 and E1 have the same names, but it'll be clear from the context which space we're talking about, right? If E1 is written this way, then you know it's in R2. If E1 is written this way, then you know it's in R3. So this is the first standard basis vector, and this is the second standard basis vector in R2. This is the first standard basis vector in R3. This is along the x-axis. This is the second standard basis vector in R3. It points along the y-axis. And this is the third standard basis vector in R3. It points along the positive z-axis. So here is the standard basis for R3. This is the standard basis for R2. You can certainly write down a standard basis for R4. Right, so this is an R4, and what is it? Its E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3, 0, 0, 1, 0. And E4, 0, 0, 0, 1. So those are the 4 standard basis vectors in R4. And then certainly you can go to R5, R6, and in general, En will be the standard basis for Rn.